Could the secrets of galaxies be hiding in plain sight in dust? Astronomers have just uncovered ancient galaxies and supermassive black holes cloaked behind clouds of dust. And it's rewriting everything we thought we knew about the universe. But what does this discovery really mean? Let's unpack every detail in today's video. When you think about a galaxy, one of the first things that comes to mind is a stunning, sprawling spiral disk, adorned with bright blue stars and glowing clouds of red and pink gas along its arms. And the best part is, you wouldn't be wrong. Many galaxies, including our very own Milky Way, tailor this description to the last letter, while others take on elliptical, irregular, or even peculiar shapes. Regardless of whatever three-dimensional form they take, though, one of the things that binds every galaxy together is an immense population of stars, millions or billions packed so densely that they blend into a soft, milky glow from afar. However, astronomers have recently discovered galaxies so groundbreaking that they question everything we once knew. Billions of light years away lie surreal galaxies that emit almost no visible starlight, with most of their light appearing in extremely long wavelengths, far beyond the range of human vision. What's more, they are shrouded in dust, clouds composed of grains of iron, rocky material, or carbon, yet much colder than expected. Now, cosmic dust isn't exactly what you sweep under the rug and forget about. It holds the keys to understanding our universe as we know it. Over the past decade, the National Science Foundation has funded astronomers to study how dust comes together at the atomic level and the big picture to see where stars and planets might be forming in the dusty stellar nurseries. But for all of the juicy mysteries discovered by the James Webb Space Telescope in recent times, one of the most interesting is what astronomers call little red dots. Ever heard of them? Like the name implies, these celestial objects are a class of small, red-tinted galaxies, much smaller than the Milky Way despite hosting nearly as many stars. Don't believe it? Here's something to scale with. With 10 billion to 1 trillion stars packed into a space just a few hundred light years across, their volume is 1,000 times smaller than the Milky Way. For perspective, if the Milky Way were scaled down to the size of one of these galaxies, Proxima Centauri, the closest star to the Sun, would be within our solar system. The Milky Way's supermassive black hole, Sagittarius A, would be just 26 light-years away, instead of 26,000, dominating Earth's night sky. At first, LRDs were widely misunderstood. They were first identified through photometric methods, appearing blue in the ultraviolet spectrum and red in the optical range. Surprisingly, 80% were found to exhibit broad Balmer emission lines, pointing to the presence of AGN, active galactic nuclei, and supermassive black holes at their core. However, several of their properties challenge the AGN model. For instance, LRDs display a flat infrared spectrum, lack detectable X-ray emissions, and show extremely weak time variability, features that are atypical of standard AGN observations. Another thing to note about active galactic nuclei is that they are incredibly bright because of the turbulence in their accretion disks, driven by the immense gravitational pull of supermassive black holes, the latter of which can be millions or even billions of times the mass of the Sun. As a result, much of the light from these galaxies might not originate from stars, but from the energy emitted by black hole-powered AGNs. This means that the star population in these little red galaxies doesn't need to be extraordinarily large to account for their brightness. Shocked? There's plenty more where that came from. What we also know is that these little red dot galaxies existed more than 1.5 billion years after the Big Bang and appear to host rapidly feeding, or accreting, supermassive black holes at their centers. A subsample examined meticulously showed light signatures that indicate hot gases spiraling down into a growing black hole. Why are these galaxies significant? Well, apart from the fact that these little red dots could be potential building blocks, or even the first stages in the formation of the galaxies and supermassive black holes we observe today, their discovery is also groundbreaking due to their immense distance and age. These galaxies were born in the universe's infancy roughly 13 billion years ago, when the cosmos was just a few 100 million years old. Their faint light has traveled across billions of years to reach us and offer an opportunity to study the earliest stages of galaxy formation. It's an opportunity we can't afford to slip through our fingers, as studying them will show how galaxies evolved from chaotic beginnings into the structured systems we see today. Now, I know what you're probably thinking. Why now? Why are scientists and astronomers suddenly making such groundbreaking discoveries when we've yet to conquer simpler problems? Well, the answer is actually a surprising one, and no, it's not as simple as boiling it down to modern technology. The answer, ladies and gentlemen, is dust. Yes, dust. The very building block of these distant galaxies. It's kind of ironic, isn't it? Just like how accumulated dust can disrupt the effectiveness of your favorite gadget, a little bit of cosmic dust creates a very large problem. Although dust accounts for just about 1% of the interstellar medium, the material between stars, it plays a significant role in astronomical observations. Dust often gets a bad reputation because it absorbs and scatters visible light from distant galaxies and stars, making them challenging or even impossible to observe with optical telescopes. Curious about what causes this scattering effect? Commonly known as reddening, dust scatters blue light, shorter wavelengths, more effectively, thus making objects appear redder. This phenomenon is similar to why sunsets look red, as Earth's atmosphere scatters blue light, leaving behind the longer red wavelengths. So you see, cosmic infrared radiation paints a picture of the universe's history, from a few 100,000 years after the Big Bang to the present day. However, dust within our solar system emits light at the same wavelengths, interfering with and distorting this cosmic image. That's why we had no idea about this groundbreaking discovery, and so many secrets were just waiting for us to be discovered. Nevertheless, dust is more than just a pesky layer that hides the universe's secrets. Dust can be compared to grains of sand on a beach. Some may have formed nearby, originating from relatively recent processes, while others have traveled vast distances, bearing the marks of their long and intricate histories across millennia. Understanding their distribution provides crucial insight into the dynamics of our galaxy, as regions dense with dust often signal intense star formation activity, while gaps in otherwise dusty areas suggest a supernova explosion may have cleared away the material. Did you know dust also plays a vital role in the life cycle of stars? It marks both their creation and their demise, making it an essential component of cosmic history. Dusty regions in space are also the birthplaces of cosmic chemistry, producing molecules like graphite, the same material found in pencils. When stars reach the end of their lives and explode, they release dust into the cosmos, where it is recycled to create new celestial structures. So, yes, everything in the universe, stars, planets, asteroids, comets, and even life itself, originated as tiny grains of dust drifting through space. This interconnected cycle underscores the profound truth that the building blocks of life were forged in the hearts of dying stars, connecting us all to the cosmos. Astronomers can observe stars within galaxies actively producing dust, while other dust particles might date back billions of years. These ancient grains have undergone a complex journey of growth, erosion, freezing, and heating as they traveled through the cosmos. But thankfully, there is a way we can make the cosmic dust work for us. The most effective way to differentiate the Milky Way and solar system dust from the broader universe is by combining diverse data sets from multiple telescopes into a single, cohesive model. This approach involves utilizing historical data from satellites like JWST's Akari, NASA's IRA, and the upcoming SphereX, which is set to become operational this year. These datasets span decades of space observations, but until now, they have only been analyzed individually. Integrating them into a unified framework represents a groundbreaking step forward in cosmic research. Should researchers succeed, they will be able to present three-dimensional maps of space for different epochs. This way, we can study the development of the universe over time, but for now, we have JWST's infrared technology to thank for penetrating this dust, okay? Remember when we told you regions dense with dust usually signal intense star formation activity? Unlike visible light, which is easily scattered or absorbed by cosmic dust, infrared light can pass through these dense regions, allowing JWST to peer into areas that were previously obscured. This was the key to uncovering the little red dots galaxies hidden behind thick layers of interstellar dust that block their light. Additionally, infrared light operates at longer wavelengths, which means it interacts differently with dust particles. While visible light is absorbed or scattered, infrared light can slip through, revealing what's hidden. For JWST, this means being able to detect faint and distant light from galaxies that formed over 13 billion years ago during the universe's early stages. All that was required to determine the composition, temperature, and activity within these galaxies was simply analyzing the infrared signals. Don't take this to mean we have all the answers, though. The striking presence of supermassive black holes has taken humanity aback. You see, all black holes have event horizons, which are light-trapping boundaries. This means any light associated with the little red dots comes from the surrounding material, not the black holes themselves. However, the red dot black hole regions appear distinct from other quasars, even those observed by James Webb in the early universe. They emit unexpectedly high levels of ultraviolet light, and their supermassive black holes are astonishingly massive. What's more, black holes typically grow alongside their host galaxies, but these red dot black holes seem disproportionately developed compared to their baby galaxies. So, yes, their mere existence challenges previous theories, as scientists did not expect black holes of this size to form so early in cosmic history. Before we go into the next juicy secret, have you ever come across headlines claiming that cosmology is broken since the James Webb Space Telescope began detecting these ancient little red dots? Well, the reason why everyone was so worried was because even the greatest of scientists were at a dead end. They pondered tirelessly on how early galaxies could accumulate large enough stellar populations to emit crazy amounts of light when the universe was only about 13.8 billion years old, 12% of its current age. However, further analysis has proven that these galaxies are not anomalies, but instead represent a previously unrecognized stage in galactic evolution. The James Webb's ability to observe these galaxies in the infrared spectrum, something older telescopes like Hubble couldn't do, has provided scientists with new insights into their structure and formation. The early existence of these galaxies aligns with models of cosmic evolution, but the key difference is that the process was more complex and occurred earlier than originally thought. While these findings have strengthened cosmological theories instead of overturning them, not all questions about these little red dots have been answered. One ongoing mystery is the absence of galaxies with similar properties in the local universe, particularly those that are less redshifted. One explanation is the inside-out growth of galaxies, where star formation spreads from the core outward. Over time, fewer supernovae near the central black hole deposit gas, reducing the dense gas and dust that obscure the AGN. As the black hole pushes away surrounding matter with powerful plasma jets, the galaxy brightens in blue wavelengths and loses its red appearance. The idea of AGN obscuration is also supported by the lack of high-energy X-ray emissions from these ancient galaxies. Unlike nearby feeding black holes that emit bright X-rays, dense clouds of gas and dust likely absorb the X-rays, suggesting the black holes and little red dots are heavily shrouded. So, what can we make of this? The mystery of little red dots lies in two possible explanations. They either host supermassive black holes or an unusually high number of stars within a compact space, each with challenges. Evidence at the moment suggests that, like many large galaxies today, early universe little red dots likely harbor supermassive black holes millions of times the sun's mass. This is supported by their spectra, which reveal gas moving at thousands of kilometers per second, consistent with material spiraling near such black holes. Yet, it raises one major problem. Black holes typically emit X-rays due to the intense radiation from infalling matter, but most LRDs show no X-ray emission. Adding to the intrigue is the fact that nearby galaxies show a proportional relationship between black hole mass and their stars, with black holes accounting for about 0.1% of stellar mass. It's a far cry from little red dots, whose ratio could reach an astonishing 40%. Shattering all known scaling relations and raising even more questions about their co-evolution. So, where do we go from here? Is there more to these little red dot galaxies than meets the eye? Or are we missing one key piece to understanding the bigger picture? Share your thoughts in the comments, and don't forget to leave a thumbs up and subscribe to the channel. See you in the next one.